All right, we made it to the last day, and here's the first of two videos that we're going to do. This video focuses on compact sets, which I really think is one of the more interesting ideas in all of analysis. And we're taking this idea of metric space. We're trying to generalize some of the things that we've seen. So really what we're doing in compact sets is we're trying to generalize the idea of an interval. And so we know that back in earlier in the semester we talked about continuous sets. When we had an interval, we knew certain things were true, like the extreme value theorem and the intermediate value theorem and stuff like that. So we're trying to say what sort of things might behave like an interval in this more abstract world of metric spaces. You can't just say every number between A and B because you could be in a metric space where that phrase doesn't make any sense. So we have to somehow phrase things in terms of sets and open sets and distances between points and balls and open balls and things like that. So that's our first question here, interval. And then in the next video, we'll take this idea of interval and then say, well, how should we think about continuous sets in this setting? But when we think about compact sets, the real thing we should be thinking is in the traditional setting, like in R2, for example, a compact set is just some sort of set that is both closed and bounded. So we wouldn't want this to be a compact set. It's not very compact because there are points around the outside edge that aren't contained in it. We also wouldn't want some sort of infinite set to be compact. That's not compact by even the English phrase compact. Okay, so we should think closed and bounded. And the big theorem at the end of this, at the very end, is if we have the right type of definition for compact and we have kind of the right additions to our set, then every closed and bounded set is compact, and every compact set is closed and bounded. The two mean the same thing under the right conditions. But we're going to have a very different definition for closed and bounded. So our definition we're going to use is not going to be closed and bounded, and it's actually going to be pretty uncomfortable to begin with. But I hope that you all get a hang of it, because it really is one of the kind of neat moments, I think, in mathematics where we have a non-intuitive definition, but it's really, really useful for proving theorems. And the more you prove theorems, the more you kind of start to get a grasp over what this definition is trying to tell us. But in order to understand the definition, we have to know what a covering is. And a covering of some set E is just a collection of sets. A covering of E is some sort of set of sets. So I'll put V, and I'll put a little alpha here. And alpha could be an index, so this covering doesn't have to be finite. It doesn't even have to be countable. For example, we could be dealing with the real numbers, and every real number could have its own set. So covering of E is V alpha if we took the union of all those V alphas and E is contained inside of that. So think of that like if I took that picture, we got some E that looks like that. And then what have we done? We've put a bunch of sets here. And if we put enough sets so that every point in E is in one of the V alphas, then we've covered E. So now I've covered it at that point. Okay, so that's the big idea of a covering. And then there are, of course, two side things that we'll need. Well, an open covering is exactly what it sounds like. And an open covering just means that every one of these V alphas is it looks like I wrote a for all, doesn't it? Every one of the V alphas is an open set. So an open covering is just a covering made up of open sets. And then a subcovering is also kind of what it sounds like. And then I guess most people say cover or subcover. I almost like covering. It sounds like we're doing something, but let's call it a subcover. A subcover is a subset of V alpha of the set that still covers E. So in my picture I had earlier, we might have something like this, and maybe I've got some sets like this. Let's draw them. I'm going to draw them with solid lines, even though we'll pretend that they're open. So we'll draw one like this, and one like this, and one like this, and one like this, and one like this. And then what you realize is that, well, I could make a subcover by deleting this one and this one. So I could have deleted those two and just left the others, and then had this one, and that would have been a subcovering. So I didn't need all of them to make the covering. So that's the big idea of a covering and a subcovering. And this brings us to the definition of what it means to be compact. And what it means to be compact is, we'll say H, and H is the letter our book likes to use. Some letters, some books will use K or other letters. H is compact if every cover has not every open cover, I need to make sure I use the word open. If every open cover of H has a finite subcover. So H is compact if every open cover of H has a finite subcover. Okay, so this seems a little strange. This doesn't feel like a good definition for an interval. But let me just point out a couple things real quick. So first, if I take 0, 1 without including 0 and 1, this one is definitely not compact. And why is that? Well, if I had 0, 1, then I could take a cover that looks like this, and maybe I'll let my cover, I'll use kind of this fancy V. I think it's actually supposed to be a Greek letter, nu, but okay. We use the fancy V. Will be this set. It'll be the set Vn, which I'll call Vn, the set from 1 over n to 1 minus 1 over n. And that's all the Vn is. And then what you'll notice is that these Vn's definitely cover 0 to 1. So if I come here and I have 0 right here and 1 right here, then what are my Vn's doing? Well, V1 is dumb, and so is V2. But V3, we go from 1/3 to 2/3. And then V4, we go from 1/4 to 3/4, and then 1/5 to 4/5. And what you'll notice is that our covers keep getting successively bigger and bigger, and we keep getting successively closer and closer to those outside edges. But we never actually get 0 and 1 included. And, well, I guess 0 and 1 aren't included in our picture, right? So I should have had these as open circles, because 0 and 1 aren't in our set. But but there are always numbers between 0 and 1 and the largest cover that we have. So the only way to get every number between 0 and 1 is to include all of them. So we must include an infinite number. Because if we had a finite number, we would have stopped at some point, and then whatever that stopping point is, we would have had some numbers in between here, because it would have had some epsilon distance. So 0, 1 is definitely not compact because we can do this trick. But what you'll notice is that once we include 0 and 1, then all of a sudden this trick that I just used right there is not going to work, right? So if I do 0 to 1, then that trick I did just a second ago won't work because I have to include 0 and 1 somehow. So if I try that same trick where I'm doing a bunch of things that look like this and I'm getting very close, well, at some point I've got to include 0. So that means I got to have an open set around 0, and that means that I can stop at whatever point that is that we have here. And also, I'll have to go around 1 so I can stop here as well. So I just have to include these open sets until I get close enough to 0 and 1 that the set that includes 0 and the set that includes 1 cover the rest of my set. Now, This hasn't proven that 0 and 1 is in fact compact, because maybe there's something else more exotic and more creative that I could have done. But this just kind of shows you that that trick that I used the first time doesn't work for 0 and 1. And in a sense, what we'll see is that this idea of covering and subcovering, that if you don't have a finite subcover, that's going to be connected to the idea of a sequence that you can keep getting. As there are points on there that you can get progressively closer to forever and ever, that are kind of on the boundary. Versus if it doesn't have one, then you're not allowed to do that. That sequence point, the point that the sequence is converging to, has to actually be in the set itself. Okay, so this is just kind of to get you a little bit of a feel for that. And so I have a task for you I want you to do. This is where we'll probably start class when we come to class on Tuesday. And that is, I want you to think of this set, the set 1 over n. And so we have talked about this set a lot. So here's 0 and here's 1. And so the set 1 over n is, we have that point, that point, that point. And so it's this set of all the points that kind of converge towards 0. So I want you to create an open cover of that set that has no finite subcover. So just create your own open cover that works, that you can't take you can't take a finite number of them and cover the whole thing. And then what I want you to do is try to think about this, although this is harder to prove. So proving it might be a challenge for most of you. If you can prove it, I'll give you 2 thumbs up and I'll be really proud of you. But even if you can't prove it, say, is there some sort of convincing argument, some way you would talk to someone that proves that if, oh wait, this didn't copy correct. Okay, this union 0. So sorry, so we want this set E from 1 over n, we want to add 0 to it. So if I add that 1 point, just add the limit point to it, then all of a sudden I believe that it must have a finite subcover. And so I believe that this second one with 0 included is compact, and the first one with 0 not included is not compact. So I want you to do these just to practice using these covers and subcover definitions. And now we're going to prove a bunch of things today, and a couple of these proofs are going to be challenging, but all of them are kind of things that I think we can understand, and I want you to take the time to really think through these proofs, because in so doing you're going to really understand this kind of dance of how we use coverings and subcoverings to prove things about compact sets. So let's start with this first theorem, and that says a compact set must be closed. So how am I going to do this? Well, I'm going to assume that H is compact and not closed. So H will be compact and not closed. And then what we'll do is we'll let Xn be a set in H. Let Xn be a sequence in H such that Xn converges to some X that's not in H. And we know that this has to exist because it's not closed. If H was a closed set, then every sequence would have to converge. Every convergent sequence would converge to something in H. So we're going to find one of the convergent sequences that converges to something outside of H. Well then, what I'm going to do, and I'll kind of draw my picture over here. So I've got my set over here. H. And then I'm going to have X on the outside of H, and then I'll have my sequence kind of converging to it. And then what I'm going to do is I'm going to create an open cover, and my open cover is just going to use this point right here, and it's going to take every point possible, and it's just going to say, well, let's just create an open cover that doesn't reach this point X. So every point I'm going to create an open cover that doesn't reach this X value right here. So this X value I'm going to exclude. And the way I'm going to do that is I'm going to define the radius to be something very specific. So I'll let the radius of Y equal 1/2 the distance between X and Y for all Y in H. Now it's obvious that this must be a cover. So it's obvious that the balls with radius Y centered at Y is an open cover of H. Right, and this is a pretty clear thing because y is in one of these balls, right? So each y value I could possibly choose has a ball that it's the center of, and so it's in one of them. So every h point is in one of these balls. So if I take all the balls together, I get an open cover in H, but notice by creating an open cover of H, I have implied, because H is compact, that there must be a finite subcover. And so my finite subcover is going to have some finite collection of radiuses, but because it's finite, I can pick the largest one. So because I have a finite subcover, I can let R be the smallest R sub y in the finite subcover. So whatever our finite subcover is, we had like n, we have n of these open sets left, and each one has a radius, and just pick the smallest of those radiuses. Okay, but then what I'll notice is that what happens if I take a ball of that very smallest radius and put that ball around x? Well, each r went halfway between x and y. So if I take a ball of that radius and put it around x, and so again, that's this ball right here. So if I take that ball and put it around x, then what do I know? Well, that ball can't have anything in h in it. So if I intersect that with h, I have to get the empty set. That ball can't have any h's in it, because if it did, right, if it did, then we would have things that aren't in one of these balls in one of these balls in our finite subcover, and then our finite subcover wouldn't actually be covering H, right? So the fact that this finite subcover isn't covering H, then and every point is further than this R away, then I know it must be non-empty. But what does that mean? This creates a contradiction, because that means that because the sequence is converging to that X, there must be points in that sequence that are no longer in H. But this means there must exist some X in that was not in H. And that's where we get our contradiction, because that X in had to have been in H. So what's at the heart of this proof? The heart of this proof is I was able to create an open cover using this point that was outside of H as kind of my reference to make the sizes of each of these. But then once I reduced it to the finite subcover, which is what compactness says, then all of a sudden that means that this X had to have been surrounded by an open ball. And since it was surrounded by an open ball that's not in H, then there had to be points in the sequence that are not in H. But that contradicted the idea that contradicted the fact that the sequence was entirely contained in H. Okay, so there's a lot going on here, but I want you all to kind of notice how we used the open cover. So we created our own open cover. We kind of did so in a very clever way, but then from that open cover, and remember, this open cover was huge. Every single point in H had its own ball in this open cover. So if, for example, if we are in the domain R2, then this open cover has uncountably many things in it. But because it's compact, I was able to reduce it down to a finite number. And once it's a finite number, I can take mins and maxes. And that's what happens a lot in these proofs. All right. Let's come to another proof, which says that if I have a compact set, so if I have some compact set, and then I have some closed set inside of it, that set itself must be compact. Well, how do I do this? This one's actually going to be quite simple, and I'm not even going to write out the whole proof. So I'm just going to say let some set V alpha be an open cover of this smaller set, which I'll call E, and we'll call H our big compact set, be an open cover of E. And then what I'll notice is this: I will take one more set, then I will define. I'll create one more V, and we'll just call it V prime, and we'll let that be X minus our E. But because E is closed, This is also open. And then what I'll notice is that if I take all of these V alphas and add this one additional set to it, this covers H. So that means there is a finite subcover. But then that finite subcover that covers H also covers E. So there you've got it. So we were able to just add one set. And so what's the big idea? Well, we have a bunch of sets covering E here, and then I took one additional set, which is the set that's outside of E, which had to be open, and that means H had to be included by that set plus all the ones that cover E. And then we reduced down to a finite number, but E had to have had a finite number as well if H has a finite number. Okay, I think that's a nice proof. Let's come to another one that'll be pretty quick. Every compact set is bounded. Now all we're going to do here is we're just going to let X be some point in our set H. Let X be an element of our compact set H. And so let X be an element of our compact set H. And then what I'm going to do is I'm just going to create an open cover of balls around this point H, X. Then if I just take the set of balls of radius n about X, such that n is a natural number, this must cover H. Why does this set have to cover H? Well, all these balls are is the collection of everything within a distance n of X, and we know that every point has a finite distance to every other point in the set. So every point in the set has to be in one of these balls, as if you keep going out forever. So this must cover H, but what does that mean? That means there exists a finite subcover. And in particular, if there's a finite subcover, then there exists a maximum value n of a maximum n such that H is a subset of the ball of capital N of X. So we take that finite subcover, we have a finite collection of these balls, and we pick whichever one's the biggest, and that biggest one must cover all of H. But that's exactly what it means to say H is bounded. So we've proven H is bounded just because we found one ball that contains all of H. Okay, now at this point, let's take a quick jog down memory lane, and just remember, as we talked at the very beginning about compact sets, we wanted to say that compact sets mean the set is both closed and bounded. And what we've seen is that this is true in some sense. We've seen that if we use our funny definition of compactness, then that means it must be closed and bounded. So we've proven this direction, that compact sets must have this closed bounded property. It turns out that the backwards direction isn't always true. So now we'll have to spend just a moment and go through what do we have to do to make the backwards direction true. So we have this funny definition, but I want to show you something about the funny definition that comes up with one metric space. And you might guess there's one metric space we've been using for all of our contradictions so far, and it's the discrete metric space. So we'll do R with the discrete metric. Just a reminder from last time, what is the discrete metric? This is the metric where 2 points are a distance of 0 away if they're equal to each other, and they're 1 away if they're not equal to each other. But let's also bring up another point that we had, and a second point that we found last time was that every individual point itself is an open set. That's because each individual point has the ball of radius, any number less than 1 is contained in that set. That's because the ball, the open ball of, say, radius 1/2 of X is equal to just that point X. So that point all by itself is an open set. Well, this is how we come up with a space that is both closed and bounded, but not compact. So it's pretty obvious that the set 0 to 1 is closed and bounded, but we can make an open cover that looks like this, but just the set made up of just the individual x's, such that x is a number between in 0 and 1 is an open cover. But notice this open cover has no finite subcover. In fact, it has no subcovers at all, because this is just, if we take out any single point, all of a sudden it doesn't cover it anymore. Okay, so this just shows you that this closed and bounded requirement can be a little strange in strange spaces. So we need to add a couple things to make this thing run. And the way we'll make this run is, first we'll define the word separable. And all the word separable means is that there is, we'll say x, a set, x is separable if there exists some set z in x, so this z is a subset of x, such that the following is true, such that z is countable and z is dense in x. Okay, countable, we know, we've talked about that a little bit, but what does this denseness mean? Well, what it means to say z is dense has a couple different definitions. One definition would be that for every x in x, there exists a sequence, say z of k, in z, such that z of k converges to that x value. So in other words, every single x value, you can get z values as close to it as possible. Another way of saying this would be that for any ball, any open set, actually it doesn't have to be an open set, a ball, let's call it an open ball, for any ball of radius epsilon around x, there exists some point z in z, that's not the integers, in z, such that that little z is in the ball around radius of epsilon of x. That means if it doesn't matter which point you choose, if you put a little ball, it's around it. So there's one example that we will think about more than all of the others, and that's the example of the rational numbers. We've already seen the rational numbers are dense in the real numbers. And what does this mean? Well, it means that if I put on a number line, if I pick any number that's not a rational number, like pi, well, I can take a sequence made up of just rational numbers that converge to pi. And I've already showed you one of the ways you can do that. You can just take, each sequence can just be the first n digits of pi. So xn is the first n digits of pi, x100 is the first 100 digits of pi. Then that's going to converge to pi, but every number itself is rational. So it's a set of rational numbers. It's a set of rational xn's that converge to this non-rational number pi. Another way of thinking about this, though, is that if I take pi, or any irrational number, pi is a good irrational, but if I take any irrational number and draw some sort of ball around it, a ball of radius epsilon around pi, there must be some rational number in here. So there's some rational number that fits inside of that ball. And we can show this. We proved that if you take any two real numbers, that there had to be a rational number inside of it. And so this is what it means to be separable. And so the example that we think about most is the rational numbers. And in some sense, you have to have some countable set like the rational numbers inside of your metric space in order to make this closed and bounded proof that we want run. But it turns out there's also a lot of other things. So any higher dimensional set like R2, that that also has rational numbers. If you take the two-dimensional rational numbers, those are also dense and those are also countable. So there are lots of sets. In fact, if you take like the collection of all polynomials, then those have you can use rational coefficients, and those have a set. Those are separable. So lots and lots of things that we would be interested in studying are separable. Okay, so this brings us to this theorem that I'm really just going to kind of wave my hand at. This was a theorem. It's named for the mathematician Lindelöf, who I don't know much about. Maybe I should have Googled him. I'll let you Google him and find out if there's anything interesting about him. So Lindelöf says that if we have an open cover, then you have to have a countable subcover. And so what that means is, as long as you have this separable metric space, every open cover had to have had a countable subcover. So here's the idea of my proof. Not my proof, but the textbook's proof, but really kind of, this is the idea of the proof, but I'm not gonna go all the way through it. But the point is, you take every x value in your set, and you take some open cover. So you take some open cover. V alpha is going to be our open cover. Let's go back. It's going to be our open cover. And then if I take that V alpha, then that means we've got some kind of open set here, V alpha. But then what I'm going to do is I'm going to say that, okay, then there must be some rational point, or not rational, there must be one of these separable points. If this were with the real numbers, then these would be the rational numbers, but there must be some value here. So one of these z type things that has a ball that goes around it that contains x, such that x is inside of it. Okay. Well, that's great, and not only that, we're going to say that this ball has a rational width to it. And then what we'll do is, well, every x has one of these, so we will just identify each V alpha with this ball with the rational coefficient of my kind of rational of my countable set. And then what you see is that these things have to cover, and so these things have to cover, but because we've made a one-to-one correspondence here, these have to be countable, because we've only got one for each element of a rational set, so these also have to be countable. So that's at the heart of the proof. The details are a little bit messy, so let's just think about the heart of the proof and move on to the big one, the one we really want to prove today. And that is the Heine-Borel theorem. And so Heine-Borel is kind of one of the big theorems that you learn in analysis class, and it's one that people talk about a lot in mathematics because, I don't know, one, it's an impressive proof, and there's a lot going on. But so we have to have two properties for our set. The set has to be separable, and so we just talked about what that means. It needs some sort of rational subset inside of it, and it has to have this Bolzano-Weierstrass property. So that just means that your sequences have to have convergent bounded sequences have to have convergent subsequences. Okay, so let's go through Heine-Borel, and I think using that last Lindelof theorem, I think we'll be able to prove this eventually. Okay, so what we're going to do is we're going to do it by contradiction. So we'll let V or nu, be an open cover with no finite cover. Oh, by the way, before we start, we're assuming that H is closed and bounded, and then we're proving that it's compact, because we've already gone the other direction. So far, we've already shown that compact means it must be closed and bounded. So what we're really trying to do is backwards. Okay, so we're going to let H be a closed and bounded set, and let nu be an open cover with no finite cover. And then I will give that a fancy name. Nu is going to be my V sub alphas, but then what I know from the last theorem is that there exists a countable. I'll tell you what, let's write this over here on this side. Then there exists a countable subcover which I will call v sub k, such that k is a natural number. So now we're able to count all of these. But what that means is that h is a subset of all of these v sub k's. So h is a subset of the union of all of these v sub k's, such that k is a natural number. Now, the advantage of having something countable is that we can think of this as a countable union, and we can think of this union as sequentially getting larger and larger one after another. And so we can do this trick that we've done a lot this semester, and that is we can create a sequence xk such that each xk is an element of h minus the union as tell you what, let's switch my letter here. I'll call this xn, such that k goes from 1 to n of v sub k. So what we're going to do is, well, we know this union has to have no finite subcover. So that means if I stop at any point, if I stop at n, then that would be a finite collection of them. So there have to be some points in H that aren't in this union. So I'm just going to let X be one of those points in H that's not in my union. Well, what do I know? Well, I know from the Bolzano-Weierstrass theorem that this thing is both, it's bounded. This thing is bounded, and so it has to converge to some more thing in H. So Bolzano-Weierstrass says that there must be some subsequence that converges to X inside of my set. But then I also know that because these sets are a cover, that means that there must exist some n in my v sub k's, such that x is in that v sub capital N. Well, okay, well, now you can see where my contradiction is going to come from. So without belaboring the point too long, you can see that my contradiction comes from the fact that well, our limit point is in H, and so it's in one of these subcovers, but we're saying we don't have a finite number. Well, but we're saying each xk is in H, but not in one of these. Well, you see that at some point we have to be inside these open sets. So this is a contradiction because there must exist some point m such that for n greater than m, x sub n is in this v sub n set, because the limit point is in the v sub n set. So at some point, my sequence points also have to be in this limit set. But this contradicts the fact. This contradicts the fact that xn is in H minus the union as k goes from 1 to n. The v sub k. So we just keep going long enough, and we eventually get something that's not in this union. That's in this union. It's not allowed to be not in the union. Okay, so this is the Heine-Borel theorem. Again, we're kind of using the same few tricks over and over again. We're creating covers, and what we notice is that if we want to do a contradiction with no finite subcover, then that means you can create a sequence of things that are outside your cover, and then do something with the limit of that sequence. And so we've done that trick a couple times now as well. There's one last theorem, and it just says that, well, we knew way back when that if we were continuous on an interval, that we should have been uniformly continuous on an interval. Well, the same is true with compact sets. So if E is compact, and F is continuous, then F must be uniformly continuous. And how do we do this theorem? Well, all we simply do is continuous just means that for every epsilon greater than 0, and every epsilon over 0 and every x in E, there exists a delta greater than 0 such that if the distance between x and A is less than delta, then f of x minus f of a is less than epsilon. Oh wait, I should have used the distance notation again, and we should use our second letter of distance. Sorry, I get tired as well, and that's less than epsilon. I probably should have also made this a, right? So it'll look a little bit better, right? So if we take some point in E, then every point in E has its own epsilon. And so this is what it means to be continuous. So if you'll remember, uniformly continuous means that we want to move this for all A back to the end, right? So we want to say there exists a delta that works for every value. Well, all we have to recognize is that if I call this delta a function of A, then I can notice that if I take the balls of delta A around A, these must cover E, but then if they cover E, that means there's a finite subcover of E. So again, the same thing. Once you know it's compact, then you can move from a cover to a finite subcover, and once you have the word finite, then that means there must exist one delta equal to the minimum of the deltas in the finite subcover. And I'll let you finish that proof in your mind right now, but then what you can recognize that now that single delta is now enough that it works for every A. So if I put this delta right here, then there, for all epsilon, there exists this delta, which is the minimum of all the deltas in the subcover, such that for all A in E, rho of x and A being less than delta means tau of f of x and f of A is less than epsilon. So you can see that this we were able to have one universal delta that worked for all of them. Okay, I said a lot, and I hope that you're starting to get an idea. You feel like you're speaking gibberish after a while. You're saying covers and subcovers, and it feels like a strange thing to be saying, but I hope that we're kind of at a point where it's maybe we've gone through enough of these proofs. This idea, this complex definition is starting to internalize a little bit. We've got one more video after this. We're going to talk a little bit about continuity and how to think about continuity in a metric space. And that also, too, is going to have to do with open sets. So I'll see you there for the last video of this.